Hey guys, welcome back to my channel. I'm Anay Gupta and I'm so glad to have you here today. Well. October November exam season is upon us and I'm pretty confident you'll do well. The question, however, is are you confident of yourself? Truth be told, confidence stems from certainty in your preparation, of looking at every possible question you can imagine and every possible nuance that you can go through. But if there was one paper where you didn't know what to expect, it was the physics practical paper. And for someone like me who's gonna go all out to achieve that 40 on 40, it was this one question that gave me the thrills. Yes, the last part of question 2, the sources of uncertainty and the improvements to the experiment to mitigate those uncertainties. Most of us really study physics in a very theoretical fashion, and that is why we're not able to develop these pragmatic application skills about thinking as to why this experiment may not be feasible or why it may not be very accurate. But don't you worry, I've got you covered. During my AS level preparation, I went through a lot of these past papers to try to understand what the examiner is really looking for. And in this process, I found a few common points that you could use to score these 8 marks. But before we proceed with this video further, a big shout out to Neev who's helped me as the scriptwriter and content head for this channel. He's helped by compiling the notes you're about to see in this video. Go follow him on LinkedIn. The link is in the description below. Also guys, please be a part of this wonderful community we are building by joining the Discord server with the link in the description. Especially with this exam season, the AMAs and study sessions will be really fruitful. Okay, let's get to the crux of it and let's see some very common sources of errors and their improvements in the AS level practical exam. Now, make note of one thing, that the improvements might include apparatus that you have not worked with in the lab previously, but just understand what they are and you can use these apparatus as improvements in different contexts as well. So the first type of experiment is a timing and oscillation experiment in which there is a pendulum and you have to swing that pendulum and record the time period for one oscillation. So what do you do regularly? You take the time for 10 oscillations, divide it by 10 and find the time period for one oscillation. However, you could write that the event is still quite short and that is why the reaction time is very significant in starting and stopping the stopwatch. So what's the solution? You film the video with the timer in the camera frame and then you view the video frame by frame to check at what time did the pendulum come back to the mean position. This is the mean position. And then you see the time reading on the stopwatch and you can understand that okay, at this point the pendulum came back at the mean position. Alternatively, you could use a position or a distance sensor and find out at what time was the pendulum at a distance of 0 at the mean position. Okay, or there's another option that they use light gates. What are light gates? Light gates are some sort of a technology that can start or stop a timer when the object passes through them. Okay, so there's a beam of light over here at the mean position. Okay, pardon my drawing. And when the pendulum cuts this light gate, when it passes through that, the timer will start, and then when it comes back, okay, the timer will stop. That's half a oscillation. Okay, that's half an oscillation. So then you could just multiply that by 2 to find the time period for one oscillation. Okay, so that is what you could do. You could use light gates. Now, the second problem could be that it's difficult to measure time because you have to view the object as well as the stopwatch simultaneously. However, I would not recommend you to use this source of error, but again, the improvement would be the same as above. Now, the third problem could be that when you are exerting or releasing the bob, it is, you might exert some kind of force while releasing it. So it's difficult to release an object without exerting some external force. And the solution to that is you could just hold the object against a card and then release it. So it's impossible for you to put pressure through that card onto that object. Even if you put, it will be very negligible. Or alternatively, if you're dropping some object from some place, if they say to drop a ball vertically downwards, in that situation you could use an electromagnet. When you turn off the electromagnet, the ball will fall down. So that is also a solution you could use. Okay, then the next problem could be difficulty with measuring t with reason. For example, it is difficult to judge when an oscillation starts, ends, is complete, right? Because you can't see the mean position with a naked eye. So the solution to that is to use the fiducial marker, and then you can now see the mean position and see when you start the timer, when the pendulum passes through the fiducial marker, and stop when the pendulum passes again back through it. Okay, the next source of error is pretty self-explanatory, that the object movement is affected by the wind. And the solution to that is just to turn off the fan and close all the windows so that there is no draught passing through the pendulum. But I would not personally recommend this source of error because it is something that you can avoid, and it's kind of the fault of the performer who is doing the experiment. So you could do without this. The last source of error for a timing and oscillation experiment is difficulty with the angle or point of release, because if sometimes you're asked to measure this angle theta or alpha, and it's difficult to measure that angle, and what do? You use a fiducial marker or a pointer to note the initial amplitude. So I could just make a marker like this, and I know that okay, I have to lay the string along this marker. So that is how you can ensure that the angle stays constant. Okay, the next set of errors are measurement errors, and in the lab we use rulers and protractors to make measurements, and here we can face some errors. So first error is something called the parallax error, where you can't get the line of sight to be at level with the object you're measuring. So what do? You clamp the protractor and then you take a photograph, and then you can just draw a line on the photograph and measure the height. Or you could use a thinner string, or you could use trigonometry with length measurements described. So different types of experiment, and these are different types of improvements if you're not able to take the ruler measurement correctly. Okay, the second problem is difficulty with ensuring x is horizontal. So it could be a string, it could be a ruler, it could be whatever, anything. If you're asked to keep horizontal, it could not exactly be horizontal, right? There could be some tilt to it. And how do you check whether it's horizontal? You use something called as a spirit level, okay, that can ensure whether the object is completely horizontal. Or you could measure the height at two different places from the bench. Okay, so I use a ruler and I measure the height over here and the height over here, and if it's exactly horizontal, both the heights will be equal. So that is another thing I can do to ensure it is horizontal. Now, to ensure something is vertical, okay, like for example the ruler over here, I want to ensure that it's vertical. Okay, what do? I use a set square and I clamp the ruler. So I use a set square like this, that is perpendicular to the ground, and I clamp the ruler over here. So this ensures that my ruler is now in a correct orientation. Or what I can do is use the object holder, or I can use something called as the plumb line that shows me where the vertical is. Okay, so the plumb line is nothing but a thread with a mass at the bottom of it. So the mass just falls down towards gravity, and this is exactly vertical at all times. So it's, you hold the plumb line from here and it shows you where the vertical is. Okay, and there could be a difficulty in keeping the ruler or protractor steady because our hands are just constantly moving a little bit. So you clamp the ruler or protractor. So these are some measurement errors. Next up, we have the length errors, that are errors while measuring the length of an object. So first of all, if you are using a ruler to measure some object, there could be a large percentage uncertainty. For example, I have a length of 2.5 centimeter. Okay, and I have measured that using a ruler. So the absolute uncertainty over here will be 0.1 centimeter. Okay, or let's say I have 0.5 centimeters, a small length. Okay, but now if I use a vernier caliper, I could have it to 0.52 centimeter. Okay, and the least count over here is 0.01 centimeter. So that reduces my percentage uncertainty. And if I am, for example, using a micrometer screw gauge, I could measure it to 0.523 centimeter. Okay, that is giving me an absolute uncertainty of about 0.001 centimeter. So that is kind of reducing my percentage uncertainty. Second error could be difficult to measure small change in length, or calipers or micrometer will squash the object. Okay, so between the jaws of the vernier caliper, the object could be squashed, and that is why a thickness, for example, could not be measured precisely. So instead, what do? You use an instrument called a traveling microscope, and it has a very nice accuracy, and it just measures the distance it has moved from point A to point B. The third error, which is very common, is length is not measured from the center of the bob. Okay, so if they ask you to measure a length of a pendulum string, for example, okay, so what they will ask you to do over here is ask you to measure the length of the string. Okay, they will ask you to measure the length of the string, but if we have to measure the length of the pendulum, we have to take the length from the center of the bob. So what do? You cannot use a ruler because that will give you a parallax error, and you can't really determine the center of the bob or center of a sphere. So what do? You use a vernier caliper to measure the radius. Okay, you to measure the diameter. You halve the diameter to find the radius, and the length, the new length, will be this measurement of length L plus your radius, which is the half of the diameter. So by this method, by this calculation, you're actually able to find a more accurate measure of the length. Now, table 4 shows you some general errors. The first error has to be like a constant. Okay, you have to write this in every paper. In every situation, this error will be valid, and it's a free 2 marks for you. So the error is that 2 readings are not enough to draw a valid conclusion, because there can be anomalous results. So the solution is take more readings for different values of L or M or whatever variable they give you, and plot a graph, or take more readings and compare K values. Okay, so this is the improvement. Write this and you have 2 marks sorted out for you. If a value of a particular variable, okay, whatever variable you have been assigned over your W, X, Y, Z, is very small, so the percentage uncertainty is very large. Okay, for example, a time, okay, is very small, so the percentage uncertainty is very large. You find a way to make the value larger, or use a more precise instrument. Okay, so for example, I am timing how long does it take for an object to fall when I release it to the ground. Okay, so how do I make the value larger? I drop it from a greater height, so that because of that, it will take more time to fall on the ground. Okay, so that is a way you could do that, or you use a more precise instrument as I have mentioned over here, and you decrease the percentage uncertainty this way. Now, a final table in which we're discussing other equipment or miscellaneous errors that I had encountered, and if you encounter similar situations, you can use these errors as well. So if there is an experiment with a pulley, okay, that there's a string across the pulley, so friction at pulley not negligible, so that exerts a force on the object, and what do? You apply oil to lubricate the pulley, and to decrease the friction. Next up, if you have an electrical experiment, then resistance of contacts, because all of the crocodile clips that you are using, all these contacts have some kind of resistance. So clean contacts to get rid of dust, rust and dirt, so that their resistance will reduce, and the resistance of the circuit will actually be the resistance of the load. Next, difficulty to measure volume for a transparent liquid. So there can be experiments involving volume of water in a container. Okay, so if it's a transparent liquid, then it could be difficult to see through it. So add dye to the solution to make it more colorful. If you've been asked to measure the mass of a particular object and then use a putty to stick the object, you have ignored the mass of the adhesive putty, and the improvement is simply to add the putty mass to the mass considered. Simple, okay? Next source of error is a certain reading that was skipped during consideration of the conclusion, and include any reading that was not considered for during conclusion or for the conclusion. Okay, what is okay? Sorry for the grammar here, but this is a very rare error, and I would advise you to avoid this. And a nice source of error is the last one, that object hasn't reached terminal velocity. Okay, so this comes very often in ramp experiments. So there's a ramp and there is a car or an object, and they ask you to roll that object down to the floor through the ramp and to calculate its velocity by measuring the distance and the time. And the problem here is that the object has not reached the terminal velocity yet, so it's too early for us to determine its terminal velocity by calculating distance and time. So what do? You give it more time. So how do you give it more time? You release the object from a greater height to ensure that the terminal velocity has been reached. So here are some of the more common sources of errors and improvements in the physics AS level practical exam that you can use to score those 8 marks. Make sure to be specific. So if you are saying that parallax error, okay, let's say you're saying parallax error. So parallax error for what? Okay, to measure the ruler. Why? Okay, and which variable? So to measure, it is difficult to measure W. It is difficult to measure T. So whatever variables you have been provided with the question, please use those variables in your answer. Okay. And secondly, please make sure to come up with problems that you cannot really solve. Okay. For example, the wind thing, you can solve it, right? So it's like it's your fault if you have not turned off the fans while using a card or while using a pendulum. So if the problem can be solved by you, please make sure to avoid that in your answer. Okay. But if, for example, the problem is difficult to solve, like placing the ruler vertical, okay, I cannot really solve it without using any additional apparatus, so then you can include it in your sources of error and improvement. Okay, so just make sure of these two things, and besides that, you should be good to go for your practical exam. The other questions are pretty much straightforward, but there are some nuances to take care of. I'll make a separate video perhaps on those nuances, but if you have these 8 marks in your kitty, I think you're pretty much primed for a very high score. So all the best for your practical exam, and I'm sure you'll ace it. If you like the video, please make sure to subscribe, to hit the like button, and to share it with as many people as possible. If you have any other questions or suggestions, please make sure to leave them down in the comments below, and check out Neev's profile and our Discord server. Thank you so much for watching. I'll see you all in the next video. Bye bye.